Sometimes there are underlying structures or relationships between predictor variables. For instance, new games sold on eBay tend to come with more Wii wheels, which may have led to higher prices for those auctions. We would like to fit a model that includes all potentially important variables simultaneously. This would help us evaluate the relationship between a predictor variable and the outcome while controlling for the potential influence of other variables. This is the strategy used in multiple regression. While we remain cautious about making any causal interpretations using multiple regression, such models are a common first step in providing evidence of a causal connection. We want to construct a model that accounts for not only the game condition, but simultaneously accounts for three other variables: stock photo, duration, and wheels. That is, we want the prediction price to equal beta naught plus beta 1 times condition new plus beta 2 times stock photo plus beta 3 times duration plus beta 4 times wheels. So y hat equals beta naught plus beta 1x1 plus beta 2x2 plus beta 3x3 plus beta 4x4. In this equation, y represents the total price, x1 indicates whether the game was new, x2 indicates whether a stock photo was used, x3 was the duration of the auction, and x4 was the number of Wii wheels included with the game. Just as with the single predictor case, a multiple regression model may be missing important components, or it might not precisely represent the relationship between the outcome and the available explanatory variables. While no model is perfect, we wish to explore the possibility that this one may fit the data reasonably well. So the prediction price hat equals, and then we have our same formula. We, by that I mean computers, estimate the parameters, beta naught, beta 1, beta 2, beta 3, and beta 4, in the same way as we did in the case of a single predictor. We, again meaning computers, select b naught, b1, b2, b3, and b4 that minimize the sum of the squared residuals. So here is the sum of squares for the errors and how that's calculated. Fortunately, we don't have to do that by hand. There are 141 residuals for the Mario Kart data, one for each auction. We typically use a computer to minimize this sum of squared residuals and compute point estimates as shown in the table output below. Okay. So what we would do is we would write it as y hat equals 36.21 plus 5.13 x1 plus 1.08 x2 minus 0.03 x3 plus 7.29 x4. So that's coming from this first column of the data table. Here's example 3. Write out the model using the point estimates below. How many predictors are there in this model? So again, we wrote that out on the previous slide, but we'll do it again here. So 36.21 is beta naught, 5.13 is beta 1, 1.08 is beta 2, negative 0.03 is beta 3, and 7.29 is beta 4. There are 4 explanatory variables in this model. Write out the model. Oh, that's the same one. Let's skip that. Example 4. What does beta 4, the coefficient of the variable x4, or the wheels, represent? What is the point estimate for beta 4? Okay, so the point estimate is B4, which equals 7.2852. This is how much you would expect to pay on average for a wheel. So when we look at this estimate column and we see these numbers and we put them in for these beta values, these are the estimates for the beta values. I just wanted to be clear about that. So B naught is estimated by B naught. Beta naught is estimated by B naught, which is the 36.2110. Beta 1 is estimated by B1, which is the 5.1306. So these numbers actually aren't equal to the betas because the betas represent the true population values. These numbers here come from our sample, which is an estimate of the true population values. So we put these in place of the betas, but they are again estimates, not the true values. They're just estimates. Okay, we answered that one already. Example 5. Compute the residual of the first observation using the multiple regression equation identified in the previous examples. Okay, so here we go. So y hat equals 36.21 plus 5.13 times 1, so our condition is new, plus 1.08 times 1, we have a stock photo, minus 0.03 times 3, we have 3 days duration, I think is what that means, the days, number of days, plus 7.29 times 1, we have 1 wheel. So this is approximately equal to 49.62. And I guess that's not actually approximate, I think that's equal. Okay, this is a dollar amount. This is what we would be expected to pay. Okay, and then if we want to compute the residual, what we do is we take the actual y value, or the actual price that was listed on that auction, then we subtract the predicted value. So we take 51.55, that was the actual price that was paid, minus the predicted value, which was 49.62, and we get a residual of 1.93. Here's example 6. What do the two models below have in common, and where do they differ? Okay, so let's take a look at their estimates. So the first one is just using the condition new. So I'm going to look at the estimate here. And then down here it's using all of the variables. So if I were to just compare the condition new variable with the intercept, and then down here the same thing, so just compare these two, you're seeing a little bit of a difference there. So we can also look at the degrees of freedom. They're 139 for this one, they're 136 for this one. So this would mean the n in this case is 141, and we subtract the number of rows. There's only one row that matters here, the new condition. So that's why, actually, sorry, there's two rows, the intercept row and the condition row. So 141 minus the number of rows equals 139. And then down here, we have 141. So 141 is the n value, that's the sample size, minus the number of rows, and that equals 136 for this one. Okay, let's write some more things down. So what do they have in common? For each, the condition new is significant because the p-value is very small. So if I look at the p-value for both of those, it's rounded to 0. So that means that the condition is very significant. Okay, what else can we say? In the multiple regression model, which is the second table, the wheels are included and they're not included in the simple linear model up here. So in the first model, the more wheels you have, sorry, in the second model here, not the first model. In the second model here, the more wheels you have, the more you can expect to pay in the auction. But up here, we don't have that variable, so we can't say, we can't account for that price change. So let me try to write all of that down. Okay, I think I have that right now, and again, this is because the second model, the multiple regression model, has more information. So we just plain have more information here. Okay. And also over here, concerning the degrees of freedom, the more variables you use, the less the degrees of freedom. I'll put that too. Okay. Example 7. We estimated a coefficient for the condition new of B1 equals 1090 with a standard error of 1.26 when using simple linear regression. Why might there be a difference between that estimate and the one in the multiple regression setting? Well, again, because of the wheels. Right? Because without having that variable involved, you won't know what else drives the price up, right? So with simple linear regression, you've got 1090, but with multiple regression, you only have 513. So that means that the fact that the condition is new isn't the whole story behind why the price goes up. So it's actually mostly because of the wheels involved is the other major factor. When we estimated the connection of the outcome price and the predictor condition new using simple linear regression, we were unable to control for other variables like the number of wheels included in the auction. We say that the simple linear model was biased because it was biased by the confounding variable wheels. When we use both variables, this particular underlying and unintentional bias is reduced or eliminated, though bias from other confounding variables may still remain. The previous example describes a common issue in multiple regression, correlation among predictor variables. We say the two predictor variables are collinear when they are correlated, and this collinearity complicates model estimation. While it is impossible to prevent collinearity from arising in observational data, experiments are usually designed to prevent predictors from being collinear. Here's example 8. The estimated value of the intercept is 36.21. That's from the multiple regression model. And one might be tempted to make some interpretation of this coefficient, such as, it is the model's predicted price when each of the variables takes a value of 0. The game is used, the primary image is not a stock photo, the auction duration is 0 days, and there are no wheels included. Is there any value gained by making this interpretation? Well, it's okay that we say that the game is used. It's okay that we say that the primary image is not a stock photo. And it's okay that we say that there are no wheels included, but it's not okay to say that the auction has 0 days duration, because then it would just mean that the auction didn't even happen. So you would be selling this item for $36.21 when the auction had 0 time, and then no one could buy it if it wasn't even on auction. So that's the only one that's not okay to be 0 in that sense, because it doesn't make sense. So this slide basically explains that same thing. 3 of the variables, the condition new, the stock photo, and the wheels, do take value of 0, but the auction duration is always 1 or more days. So if the auction is not up for any days, then no one can bid on it. That means the total auction price would always be 0 for such an auction. The interpretation of the intercept in this setting is not insightful, meaning we can try to interpret it the way we would do with an algebra equation, but it won't make total sense in this scenario.